Hello everyone. Today we are going to learn about primitive roots modulo n. So we were all familiar with reminders and division algorithm. That is, when you divide a number, it leaves a specific remainder and a quotient. These are distinct. So when you delve deeper into these ideas, you get to congruences, you get to certain theorems, and eventually we can build up the order of an element. And once we consolidate that through an example as well, then we will proceed to primitive roots modulo n. Let's get started. So let's learn what are congruences. We say A is congruent to B modulo n if and only if n divides A minus B. There are other equivalent definitions, but we will stick to the most basic one. N divides their difference. Say for example, 13 is congruent to 1 modulo 3, and also 13 is congruent to minus 1 modulo 7. Their difference is divisible by the number inside modulo. Alright, this is very simple, but you can also understand it in the following way. The remainder when A is divided by n and B is divided by n will be same. The reason is that since you have A minus B equal to some nk and A has some nq1 plus r1 and B has nq2 plus r2, I want it equal to nk. So this is n times q1 minus q2 plus r1 minus r2 equals nk. The number on the RHS is divisible by n. Therefore, this difference must be divisible by n, and the difference must be 0 in fact, because it cannot be n or minus n. It is bounded by n and minus n. At most it can hold n minus 1, and at least it should hold negative of n minus 1. Therefore, the only divisible number by n will be 0, and hence we conclude that both remainders are equal. So this is something that we often use when we talk about congruences. Next we will learn about Euler's totient function. The function phi of n, which takes a natural numbers and gives you a natural number, computes the number of numbers coprime to n and less than or equal to n. Coprime to n and less than or equal to n. This is called as Euler's totient function. Let's take a quick example. What is phi of 12? I request you to compute this once by yourself. Phi of 12. The number of numbers coprime to 12 and less than or equal to 12. So let's enumerate the set. 1 is less than or equal to 12 and it is coprime to 12. Same goes with 5, and the next number is 7, and 9 will not be coprime as 3 is a common factor, 10 is not, 2 is a common factor, then 11. So you see, 4 is the value of phi of 12. There are several other applications of Euler totient function. It's a very interesting function. We are going to study one of its application, which is the Euler's theorem. Euler has done many things. So this is one of Euler's theorem. If you consider a number, natural number or any integer a, which is coprime to a natural number n. N is a natural number, a is an integer. Assume that a is coprime with n. Then it turns out a power phi of n is congruent to 1 mod n, where phi is the function we just studied. Isn't that quite interesting? Let's see this with an example. We are not going to substantiate it. Consider the number coprime to n. Let's say n is 12 and the number co-prime to 12 would be 5. So the Euler's theorem applied on this set of numbers would be 5 power 4 congruent to 1 modulo 12. Let's check it out. 5 power 4 is 625. And is it really congruent to 1 mod 12? For this to happen, 12 must divide 625 minus 1. Which is in fact true. 12 divides 624. Because you can find that 12 5s are 60 and 2 goes off, 12 2s are 24. So this is one example that illustrates the application of Euler's theorem. We haven't proved it. We haven't proved the Euler's theorem, but we will use in our discourse for further diving into the modular arithmetic. Alright, now we are going to observe some pattern. So watch carefully. Consider the powers of 4, 4 power 1, 4 power 2, 4 power 3 and so on, modulo 11. And let's see how its reminders behave. We will deduce certain properties from that, and we will also define a new property from that. Clearly, 4 is congruent to 4 power 1 is congruent to 4 mod 11. So I'm going to just write their reminders, because I know when I reduce it to reminders, it will still be congruent. When you write a number a as the divisor times quotient plus remainder form, then you will see that a is congruent to r modulo n, because a minus r is a multiple of n. So that's why I'm reducing it to the remainder modulo 11. 4 square, which is 16, is congruent to 5 mod 11. 4 cube, that is 64, is congruent to 9 mod 11. 4 power 4, which is 256, and that is congruent to 3 mod 11. And 4 power 5, you can compute that, it would be congruent to 3 times 4. So I can also multiply the remainder of 4 power 4 with 4, instead of directly multiplying 4 power 4 with 4. So that gives us 12, which in turn is congruent to 1 mod 11. And see what happens now. When I go to higher powers, 4 power 6, it would be congruent to 1 times 4, because 4 power 5 is congruent to 1. So when you multiply 4 both sides in this congruence equation, you will get 4 power 6 is congruent to 4. This is mod 11. And again, multiplying 4 with 4 power 6 congruent to 4 gives us 4 power 7 congruent to 16, which is 5 mod 11. 4 power 8 is congruent to 9 mod 11, 4 power 9 is congruent to 3 mod 11, 4 power 10 congruent to 1 mod 11. And here we are. You could see the entire set of reminders just repeats after 1. So when I reach 1, I get to the remainder of the first power, and then it repeats up to 1. There is a formation of cycle among the reminders of powers of 4 modulo 11. So first we start with 4, then to 5, then to 9, and then 3, and then 1, back to 4. This property is very much clear to us, because once you reach 1, you must go back to the first power, as 1 into anything is the same thing. So the first power will come back after 1, and the length of this cycle would give us something called as order of an element. Over here, the length is 5. So therefore, we say order of 4, because we are working with powers of 4, modulo 11, because we find reminders when divided by 11, equals 5, which is the length of the cycle. Or in other words, it is the smallest exponent by which I have to raise the number 4 so that it is congruent to 1 mod 11. And that smallest natural number is 5. So there are two interpretations of order of an element, and it is symbolically written as O of 4 to the suffix 11 equals 5. And this is quite important. Once you compute the order of an element, you actually compute the length with which the reminders repeat for higher powers of a certain number. By the way, we are only interested in numbers that are co-prime with the actual modulo number. We compute order of A modulo n with A co-prime to n. Suppose if it's not co-prime, then it is not much interesting. You will never attain the value to be congruent to 1. If you say some higher power A power k is congruent to 1, it just means that A power k minus 1 equals nk. Now if n and a share a common factor, then that must divide 1 as well, which can never be true. When we don't have 1, it is difficult to predict how it works. Generalizing this, we write order of A mod n equal k if k is the smallest natural exponent such that A power k is congruent to 1 modulo n. And over here we assume that GCD of A comma n equals 1. Let us study about how reminders behave for higher powers with respect to the order. As you could see, 5 is the first moment you reach a remainder of 1 modulo 11. The next exponent will be 10. So what will be the next exponent? It is going to be 15. So it is a set of multiples of 5. So when you extrapolate or collect all the terms, it will be 5, 10, 15 and so on. And hence, for any power of 4 that is congruent to 1 mod 11, and if it is a multiple of 5, it is going to be congruent to 1 modulo 11. Let's write it up. By the pattern we observe, A power k is congruent to 1 modulo n is true if and only if order of A modulo n divides k. This is due to the cyclic nature of the reminders. And remember, the order of A modulo n shall divide any such power, which means it will also divide phi of n, as we know by Euler's theorem that A power phi of n is congruent to 1 mod n. And hence we conclude that order of A mod n divides phi of n. This is a quite interesting way, because we narrow down the possibilities of order to divisors of phi of n. Let's now understand what are primitive roots modulo n. If you consider a number co-prime with n such that order of A mod n equal phi of n, then we say A as a primitive root. Then we say A to be a primitive root modulo n. What is so special about this? Well, we first observe that order must divide phi of n, which means it is always less than or equal to phi of n. So for primitive roots, it's getting maximized to phi of n. So the order will, the smallest value at which it is congruent, the power is congruent to 1 mod n, happens at the exact Euler's totient function value. In the example we studied, phi of 11 is actually 10 because all numbers less than 11 are co-prime to 11. But 10 is not the order. In fact, 5 is the order which is less than phi of n. Hence 4 is not a primitive root modulo 11. So if you work more, you will be able to derive that 4, 9, 10 are not primitive roots modulo 11. But still there are primitive roots modulo 11. For example, you can take 2, you can take 7, you can take 8. They are primitive roots modulo 11. More interesting fact is that if you take a natural number of form 2 or 4 or some odd prime power alpha or 2 into odd prime power alpha, where p is an odd prime and alpha is a natural number. Then all these values of n possess a primitive root. This is a deep theorem and requires a rigorous long proof. We will do it in later videos, but for now we will take it to be true. They all possess primitive roots. As a challenging question, try out the following. Find the number of primitive roots for each of them. Find the number of primitive roots for each of them. Each of 2, 4p per alpha and 2p per alpha. I can give you a small hint over here. Primitive roots can actually generate the entire set of coprime numbers. Say you take g to be a primitive root mod n, then consider g power 1, g power 2, g power 3 and so on up to g power 5 of n, where the last one is congruent to 1 mod n. You will be able to notice that all these numbers are actually the set of coprime numbers less than or equal to n. The reason behind that? Clearly g is coprime, so powers of g modulo n will also be coprime. But why is it having all the numbers coprime to n? The reason, it is phi of n in number. You can prove that g power I is not congruent to g power j mod n. So these are phi of n distinct numbers modulo n and they are coprime. But we also know the fact that there are only phi of n coprime numbers less than or equal to n by the definition of Euler's totient function. Therefore, we conclude that it is a set of all coprime numbers less than or equal to n. Use this to solve, while I will also explain the reason why no two of them are congruent. Suppose if some two are congruent with I not equal to j, then you will get a contradiction that g power I minus j is congruent to 1 mod n. If you assume g power I is congruent to g power j. But it is not true in general, because I know that it will be congruent to 1 mod n at first when the exponent reaches phi of n. But I minus j is clearly less than phi of n and also greater than minus phi of n. So this is never possible, and that reasons out our claim. And put out your comments in the comment box, your ideas and solutions. Let's discuss over there. Thank you everyone. Bye.